Let me see if I can get this pen to work. There we go. Okay, where were we? Okay, as always, at any point in class, if I say something that's confusing or you need further clarification, I stop and ask, does this make sense repeatedly? And sometimes it takes a little bit for our brains to catch up to what we just heard, especially when it's new material. But just make sure that you're saying like, yeah, hold on just for a second, Mr. Aguilar. Could you repeat that, or could you reword that? Because I'd be happy to do that. Okay. Okay, so let me go ahead and actually, before we jump in, I want to show you what I've added to Canvas. So can everybody see my screen? Okay. So in Canvas, under modules, in module 4, that's where we're working right now. Last time I said that there was this discussion that I was making that was going to be due Friday. I decided to push that back to Sunday to give you a little bit of breathing room, because I know that a lot of you, as it seems, are still working on the review for test 3 and working towards taking test 3, which is due Friday. So continue working, diligently on that, but make sure that you give yourself enough time this weekend, if you're in that boat, to really dive into this material on functions. Okay. And I put some handouts here that I described on Monday, what the function and graphs of common parent functions. We're actually going to be talking a lot about parent functions today. But I included another discussion here just to continue having you guys work with this material outside of class, outside of MyLabs Plus, because functions have a lot of moving parts, as I've said before. And so we're going to have to be able to look at graphs and answer questions about the graphs. Last time we talked about what the domain is, what the range is, and how you assess them by looking at a graph. So this just gives you more practice. There's a polynomial function that I gave you here, I created in Desmos, and then 4 questions about the graph that you'll have to answer. Remember to answer these in complete sentences. If you answer the question or put a response that doesn't address the question, it just sort of reframes the original question, well, then I know that you're just trying to type whatever in. I'm really looking and reading these responses to see how you're engaging with the material, how you're understanding it, to see if we are building an understanding, right? So this discussion is here. Then I have another function that I built here in Desmos, took a screenshot of it, and then I'm having you answer 4 questions about this graph, okay? So that's under module 4. And then additionally, there are some rules for transforming parent functions. Now, those words don't make any sense right now because we're going to get into that material today. But I'm going to be talking about and referencing these rules for transforming parent functions. And again, it's going to make sense as we cover the material. The words don't have to make sense right now, okay? You guys can, let's go ahead and stop the share. And let's see. Let me turn to the correct page in the workbook. Okay. So last time we were talking about section 2.3. And this was basically functions and their graphs. So we're going to see a lot of graphs today in the same way that we saw graphs last time. So if I draw them really quickly and you need a little bit more time, just let me know. But basically, we learned some terminology about functions. So we can talk about functions. Really, is this broad category of things that can be represented as equations. They can be represented as a set of ordered pairs. They can be tables. Or they can be graphs. And so usually what we're doing in algebra is connecting equations to their graphs. And a lot of times tables and sets of ordered pairs are like roughly the same thing, just different representations. Because we'll set up a table, usually an X and a Y table with some numbers in here. Let me just put X1, Y1, X2, Y2, dot, 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 because we can have as many points on this graph as we want. But usually we are connecting our equations to the graphs through this intermediate table or set of ordered pairs. Okay. So that's like the conceptual framework of how we're going to go about examining functions. And we talked about the domain of a function, which is the set of all x values. Or the set of all input values for a given function. And then we also talked last time about the range of a function, which is the set of all output values for a given function. I'm going to put f of x as an abbreviation for function. Remember that we can represent a function two different ways. We can represent it as f of x is equal to, and usually we'll write an equation over here. Or we can swap out the f of x notation and just call that y is equal to whatever the equation is.
Can you push your paper up just a bit?
Yeah.
Thank you.
So like I said, this is sort of like a mental map of this topic of functions as we've covered it so far. So this is like a review of last time, just in a picture, sort of. Today, what we're going to do is just jump right into it. And I'm going to give you guys basically a graph of a couple of functions. I'm just going to make up on the spot because we use functions and we use graphs all the time. So graphs of functions are used in daily life. And the example that I want to talk about is something like, well, we could talk about the value of an investment account. Okay, so if you are a little bit older or maybe a little bit wiser and you have a retirement account or a stock portfolio, then you might know something about the graph, examining the graph of an investment account. Or if you're sort of younger and on the edge, the frontier of new technologies and are interested in cryptocurrency portfolios have these graphing functions as well. And basically, you can think about an ordered pair that describes basically the growth in value of your portfolio, of your investment account, of your cryptocurrency portfolio. So here, what I'll say is that let's let X equal time and let Y equal the value of, I'm going to say an asset. Ooh, can't spell today. Asset, I think, has 2 T's or 2 S's. Okay. And so you can think of the value plotted against time, and usually time is the x-axis, and the value is the y-axis. And maybe you have some start time here. Let's say the moment that you start or fund that portfolio starts at time 0. So x equals 0 is going to be the beginning of time for this particular investment. And usually in real life, you might fund, let's say, in a retirement account at maybe $1,000 to start, because you had that on hand and you just wanted to throw it into your retirement account and get that started early. And then the retirement account is tied to, or is the function of, a bunch of different components that maybe is managed by a stockbroker, or there are algorithms that can manage your portfolio as well. But once you throw it in there, it's subject to market forces that are going to affect the value of your portfolio over time, or of your asset. So you could throw it in here, and then maybe in the first couple of days, the value of your $1,000 investment goes down, right? Because the market maybe took a hit, but then maybe the market's a little bit noisy and then it fights its way back up. But markets are noisy, so it might go down a little bit, it might go back up. But hopefully over time, if this is a sort of a sound investment, this goes up over time, like so, okay? If we wanted to smooth this out, I'm just gonna draw a line that's sort of a curve that smooths out this, this graph. So I'm gonna just draw something like this. And we could say that this is like the average growth of your portfolio, or its value. It's appreciating in value over time. Okay. So this is the sort of thing that in your daily life you would be examining. You know, whenever I'm looking at cryptocurrencies or my retirement, my Roth IRA account, I'm looking at graphs like this to see what, you know, every time I put money in, is that money growing or is it sort of decreasing? Especially like at the beginning of the pandemic, as a good example, the economy tanked. And so I had one of these huge dips in the value of my portfolio. But over time, those things sort of fluctuate. And if you leave that money in long enough, usually you're good. With the exception being like huge market manipulations and crashes like in 2008. But in any case, why am I talking about this? Well, because let me go ahead and draw a sketch of this again, and just the smoothed graph. So the smooth graph looks something like this, where we said that this is the value. I'm going to say y is equal to value, and x is equal to time. And let me zoom out so you guys can see this. We want to analyze the behavior of the function, or of the graph. And it doesn't have the same behavior along its entire domain. What do I mean by that? I mean that as we go forward in time, or as we go forward along the x-axis, the value of the function goes up and down, right? So in mathematics, we would call these behaviors increasing over a portion of the domain or decreasing over a portion of the domain. And so what we want to do is sort of split up the domain or cut the x-axis into segments so that we can describe where the function is going up and where it's going down, where the function is increasing and where it's decreasing. Okay, so in this, I might say, okay, our function is increasing. And again, we want to talk about the aspect of the domain or segment of the domain. So what I might do is go over here and say, well, the graph sort of looks like it's a little bit flat at first, but then it takes this dip, right? So let's say that it's flat right here. So I'm just going to put some lines right there to indicate the flatness. Okay. But then after it gets to this x value, whatever x value that is, let's say that's at x5, the graph starts to go down and then gets down to this low point. Let's call that at x equals 8. Well, after it gets down to this low point, then the graph changes direction and starts going up, sort of like a roller coaster ride. And if you are playing the market, then it'll feel like a roller coaster ride as you take these dips and as you take these swings upward. Okay. But what we'll say here is that time is never going to stop. So this axis really goes all the way to positive infinity, all the way over here. So what I can say is that for this segment of the graph from 8 all the way to infinity, well, it looks like the graph is increasing. So I'm going to say that this graph or this function is increasing from 8 to infinity. I'm going to say that this graph is decreasing right here. We probably see like the dip right here. I said at x equals 5 all the way to 8 right there, where the graph is sort of going down like a roller coaster. So I'm just going to write this as 5, 8. So it's decreasing between days 5 and day 8, decreasing in value. And when I started this thing off, it looks like it was flat or constant in value between days 0 and day 5. Does that sort of make sense? So that's what I mean by analyzing the behavior of the graph. Basically, I'm going to use the x-axis or the domain of the function to say, okay, is the graph flat? Is it going down? Is it going up? And then I need to use interval notation to write where it's increasing, decreasing, or constant. Okay, we're going to have some examples here in a second just to give you some practice. Okay, so let me draw this graph. And this is practice analyzing functions / graphs. So say that we're given a graph that looks like this. I'm going to try to do my best to write this in a way that makes sense. So -4 is there. 4 is there. Let me zoom in since I've drawn it so small. I'm going to say that this is 6. Got a point there. Got a point there. And I'm going to that's our function. So the first thing that you might want to be able to do when you examine a function is tell what the domain and the range are. So can anybody tell me what the domain of this function is? Or does anybody need some guidance or some questions about how we go about finding the domain?
Maybe it's the minus infinity and infinity.
Yeah, exactly. And how did you get that, if you don't mind me asking?
Because I use your technique, the two markers. Yeah.
Yeah. And you're basically trying to bound the graph on the left and on the right. But since these arrows imply that the graph is going to continue expanding to the left and to the right, well, that means that this graph is going to keep expanding to negative infinity and positive infinity. So that is what our domain is. Good job. Can anybody tell me what the range is? And remember, the technique for finding the range is similar, right? You're trying to find what is the lowest point or the boundary, the low boundary or the bottom of the graph versus where's the top of the graph. So if we're thinking about it, yeah, go ahead.
Is it -6 infinity?
Why -6?
Oh, I'm sorry. No, not -6.
Yeah, so it's going to be 6 here. That y value is all highlighted. So we're going to include that 6 by putting a bracket here. But then it's not bounded above. This graph is going to continue going up in either direction, but it continues going up towards positive infinity. Okay. So I find that, students find that a little bit tricky to think about what is the motion or the expansion of the function from the left to the right, and then sort of turning your brain around and saying, what is the expansion downward and upward, right? But that's essentially what we're trying to do here, thinking about movement in two directions. Okay. Now, usually you'll have questions in MyLabs Plus that say, basically, state whether the graph, well, state where is increasing, decreasing, or constant. And then it'll say something about state the open intervals. So when you're asked a question like this to state where the graph is increasing, decreasing, or constant, this statement, open intervals, is key, because when we're talking about the behavior of the graph, we're going to use nothing but parentheses. You don't have to worry about the brackets. Okay. So usually I think that it's easy for students to identify where the graph is constant. So we'll start there, and then we'll talk about where the graph is increasing or decreasing. But you can do this in whatever order. It doesn't matter. Can anybody tell me, by looking at this graph, where do you think the graph is constant? On what part of its domain? Or between what values along the x-axis?
-4 and 4.
Yeah, exactly. So it's just this region right here between -4 and 4, because if we look up at the graph, it's flat there, or as flat as I could get it, So we're just going to use parentheses to say that this graph is constant between -4 and 4. Does anybody have any questions about that? Cool. Well, where is this graph increasing? Or along what segment or region of the domain is it increasing? And these things are mutually exclusive, meaning that if you've already used this section and said that this section is constant, well, it can't be increasing or decreasing there, right? It's either one of these three or the other, but it can't be both at the same time, okay? So increasing, what region of the graph is left over that seems to be going up?
In
6 and infinity.
Oh, okay. I see what you're saying. From 6 to infinity. That's actually a good, like I like where your brain is at, but that's not exactly how mathematicians talk about this. We're saying what region of the domain is where this graph is increasing. So that domain part is the important part because we really want to see between what x values, right? So between what x values or values on the x-axis is the graph seeming to go up. So we're sort of having to juggle two ideas at once. The upward motion of the graph and basically using the x-axis as a measuring stick to say what region is it increasing. Okay, and this is going to be my rule of thumb for you, or like a helpful analogy. Imagine as we read this graph from left to right. Okay, so we're going to read it from left to right. Pretend that you're on a roller coaster. And what I want you to do every time you graph or draw a sketch of a graph and analyze it, draw this. As you start on the left side of the graph, even though this is pointing up, you're reading it from left to right. So in reality, you are going down here until you get to this point. Okay. And if we continue from left to right, this is going to be flat. So we're just going to leave it alone because we've already taken care of the constant part of the graph. So we're riding that roller coaster and it went down. Then there's a flat region. And then we can say after this point, the graph starts to increase. Okay, so I find that students find it a little bit confusing because both of these arrows are pointing up. But remember, we're reading that graph from left to right. So really, if we sort of partition or cut this graph into 3 parts now, this region of the graph is decreasing. I'll just put decrease. This middle part is constant. And this right side is increasing or increase. But what we're concerned about are the values along the x-axis. Okay, so this increasing portion, as I've labeled it over here, is only from 4 to infinity. Does that make sense? So the increasing part of the graph is above this region of the domain, from 4 to infinity. And the decreasing portion of the graph is over here from negative infinity to negative 4. And those 3 segments make up the entire domain. Is that a little bit clearer? Or do we still have some questions about it? I got a couple more examples for you guys.
I have a question.
Yeah.
In the increase and decrease, you put like a parenthesis, but you didn't put like
I didn't put a bracket.
a bracket.
Right.
So even if
For this, you're always going to be using open intervals, which is just parentheses.
sorry, I missed that part. Thank you.
Yeah, you got it. No, it's easy to forget. But for the domain and range, you have to be careful because if a value is included, you have to include that value with a bracket. Okay. I think that these take a lot of space, so I'm trying to be mindful about not putting too much on one page. Let's look at another example here. Draw my graph a little bit bigger. And this is 1, 2, 3, 4. 1, 2, 3, 4. So this is going to be negative 1. Okay. And we're going to let go and let God. Oh my God. There we go. The pink line represents the function. Remember that the coordinate space, the x and y axis, are there just as a spatial reference. But we're just focusing on this highlighted thing, right? This highlighted function. 1, 2, 3, 4, 5, and so on. Okay. Infinity is up here. Negative infinity is down there. Okay. We're going to start this thing off by always trying to assess what is the domain and what is the range of a given graph or function. So can anybody tell me what the domain is?
Negative infinity, positive infinity.
Yeah, exactly. Negative infinity to positive infinity. Does anybody have any questions about that? What about the range? What is the lowest y value that this graph goes down to?
0.
Yeah. And then what is the highest y value that the graph goes up to? Or is it bounded above?
Infinity.
Yeah, correct. So if we think about the bounding box, it doesn't seem to be bounded on the left or right because these arrows are both going diagonally to the left and to the right. So it's going to keep expanding outward. That's why the domain is negative infinity to positive infinity. As far as being bounded below, we do have a lower boundary because the graph does stop here at the y value of 0, right? This point is, we could call it -1, 0, but the lowest y value is 0. And when we're talking about range, we're talking about y values. So the lowest point is a y value of 0. And then the highest point, well, this seems to continue going up in 2 directions. So we would say that that's not bounded above. So the range stops at infinity. Never stops. Okay. Now, if I asked you over which open intervals is the graph increasing, decreasing, or constant? So let's start off by looking for, where is the graph increasing? Over what intervals of the domain?
I don't know if it will be 0 to infinity.
It wouldn't be 0 to infinity. All right. So this is how I want you guys to do it every time, right? If you have this graph, like a little sketch of it drawn, just draw a little arrow and say, remember, pretend that you're a little person that is riding this roller coaster. The roller coaster is read from left to right, and we're going down, 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 and we get to this point, and then we change directions. So then we're going up, 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 and so on. Okay. So it looks like the graph has 2 behaviors. And it looks like the graph is split right here. You might call this the axis of symmetry, right? Because at this x value, the left-hand side of the graph is doing what?
Decreasing.
It's decreasing. But then once we get past this x value, we start changing behavior, and now we're increasing.
So would it be a -1 infinity?
So we would say that the graph is increasing on this right-hand side of the graph, and that side of the graph is from -1 to infinity. Well, since we've labeled the graph already, we can see now a little bit more clearly that that left-hand side of the graph extends from -infinity all the way to -1, and that's the portion of the graph where it's going down. So we can say that this graph is decreasing from -infinity to -1. Does that make a little bit of sense? So make sure that when you draw the sketch of the graph, or in your head, if you're given a graph and you're asked these questions, it might be important to draw a little sketch and then draw these little arrows, right? I always tell students to do this exercise, and I know it's silly to think about riding the roller coaster, but it will help you each time, okay? Riding that roller coaster, it's going down, down, down. You get to a point and there's a change in direction. We're going up, 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 okay? There's only two behaviors for this graph. It doesn't look like we have a flat region of the graph at all. So that's okay. Not all graphs will have all three of these behaviors. For constant, we're going to say that there are no regions or none where the graph is constant. Right? And just for comparison's sake, the last graph that we saw, one of the last graphs that we saw, if I can remember where I put it, oh, it's on the back of this page. This graph had a flat region. So this graph did have an increasing section, a constant section, and a decreasing section. But some graphs only have a decreasing and increasing, and other graphs are strictly decreasing or are strictly increasing. Okay, so let's look at one more of these. This is one. Okay. And as always, this is negative infinity, this is positive infinity, negative infinity, and positive infinity. So we're just going to go through the same analysis. We want to find the domain, we want to find the range, just so we get used to doing that. And then we want to determine the open intervals of the domain where the graph is increasing, decreasing, or constant. So can anybody tell me what the domain and range of this graph are?
I would say negative infinity and positive infinity.
For the domain, right?
Uh-huh. Is that right?
Yeah, that's correct. And the range? The range is a little bit harder to see, I think, especially the way I drew this graph, because it looks like it's flattening out a little bit, right? Or it looks like it's flattening out up here. But, you know, if I had drawn this a little bit better, maybe I would have been very explicit. This is going to continue sort of going up, but gradually. And to the left, it's going down gradually. So you could think about it like this. If we're trying to get that bounding box, if this thing is going to continue to go up gradually, then I'm going to have to keep moving my pen upward. And if this part is going down gradually, then I'm going to have to continue moving this downward. So what are the y values that I'm going to sort of encapsulate at some point? Well, all of them, from negative infinity to positive infinity. Okay. It turns out that this is the function, the cube root of x, which if you were to graph this thing, you would get a shape. And I'm going to show you how to do this in the graphing calculator a little later on, but just as a really brief demonstration, x. If I graph this and then I zoom out to a normal zoom, let me zoom standard. Sort of has that same shape. Maybe I can zoom in. Similar shape. Okay, so we'll talk more about these kinds of graphs later on. Don't you worry your little heads about it. But let's just move on, right? Determine the open intervals of the domain where the graph is increasing, decreasing, or constant. So I'm going to give you guys about 2 minutes. Think about it, and then we'll sort of jump in and see what we think about the regions where the graph is increasing, decreasing, and constant. You guys need me to zoom in a little bit here?
And you'd still use the roller coaster analogy with this?
Every time you're trying to assess where it's increasing, decreasing, constant, I highly recommend using that roller coaster analogy.
When I do that, my arrows are all going in the same direction,
Yeah, and what direction is that?
up to positive infinity.
Yeah, so if you think about it, this graph, as you read it from left to right, looks like it's going up, 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 up. Maybe it gets steeper, but it's still going up, 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 and then it gets gradually, it goes up. So we would say that this graph is increasing along its entire domain. So it's increasing from negative infinity to positive infinity. It's never decreasing, and it's never constant. So this is exactly what I was alluding to before when I said that some functions are strictly increasing, meaning it only increases. But the idea here is that we need to be able to use that, given any graph of any function, we need to be able to use the roller coaster analogy to assess, you know, is this a strictly increasing graph, or does it have an increasing, decreasing, or constant behavior at different locations? Okay. Does anybody have any additional questions or concerns about analyzing a graph for these kinds of behaviors? Okay. Moving on. So most of the graphs that I think we've looked at so far, at least today, are what we would call continuous functions. But I want you to think, imagine that we have two functions or graphs. One describes the running, let's say, speed of an expert athlete or an elite athlete, right? One describes the speed of a novice athlete or a beginner. Okay. Then if we were trying to compare both of their running speeds or their velocities as they ran a track, we would need two graphs to do that. So I'm going to put two graphs. Okay. This is going to be my expert. This is going to be my novice. The x-axis for both of these is going to represent time. And the y-axis for both of these is going to be represented by velocity or speed. So at the beginning of the race, for instance, of this same race, they're running the same course. I'm going to say t is equal to 0 or time is equal to 0. That's the start. You could imagine that as you start a race, as the expert runner starts a race, their velocity starts at 0, correct? Right? They shouldn't be starting at like instantaneously at 60 miles an hour, right? Plus we're talking about runners, so maybe more like 7 miles an hour. They should start at 0, and the expert would probably gradually increase speed and then maybe level off at a certain point along that race to some coasting speed, some very comfortable speed. And then maybe at the very end of the race, they would stop or at some higher speed, right? And let's say that they get to the finish line here at, I don't know, maybe the race was a 10-minute race just to monitor their speed. But notice that this drawing here, this graph, the expert runner probably wouldn't tire. They know their body enough that they're not going to have to take breaks or get winded. So they can monitor themselves and they'll be able to run continuously. So I can draw this graph without lifting my pen at all. However, a novice, somebody who's very new to running, might start their race really enthusiastically, but then run out of breath and slow down drastically. And then maybe they start at this slower speed and start to slowly increase speed. And then realizing that they're falling behind, they might try to gun it again, but then get tired. And then maybe they stop here and catch their breath. And time continues going, but then they start running over here to finish. And they just finish all out, trying to go as fast as they can. Right? Maybe let me make this one a little bit curvier there. So the behavior of this novice runner is a little bit different than the expert runner. And so this is t equals 10 as well. Okay. So for this first graph, like I said, I could have drawn this graph without lifting my pen up. But with this one, I could trace the graph up to a certain point, but then I have to sort of lift my pen, put it back down, and then continue tracing that graph. Now, I use this analogy to talk about a concept in mathematics called continuity. Okay. Continuity describes whether there are any breakpoints in a graph of a function. I'm going to put f of x again for function. So you might see that in this little example that I came up with, this is a breakpoint here. And this is a breakpoint here. And basically the graph is split up into two sections. You have this section here and this section over here. Whereas there's one continuous section here. So we would say that if these two graphs represent two different functions for two different people, that this function is called continuous because I could draw it without lifting my pen. As soon as I put my pen down, I could draw the curve, and then I only have to lift my pen when I'm done with the curve. There's no breaks in this graph. We would call this one discontinuous, okay? Because it does have a break in the graph. And so in mathematics, we study these two big categories of functions, and that is continuous functions, which have really nice properties that help us with a lot of different problems, especially in higher mathematics like calculus, versus piecewise functions, which are basically these composite functions that are made up of multiple parts, and usually there's some sort of breakpoint in them. So we're going to talk just briefly about piecewise functions, because for the remainder of the semester, continuous functions basically make up the rest of our discussions. And I think piecewise functions will sort of put all the mechanics into play all at once. So let's take a look at a piecewise function. Okay. Piecewise, and sometimes they're called piecewise-defined functions. They look something like this, and I want to warn you right off the bat, these things look intimidating, but I'm going to try to break them down. Okay. F of x is equal to, and then there's this brace thing that connects different equations. So we might have 7x plus 2, and then if x is less than or equal to 0, 7 minus 7x if x is between if x is between 0 and 7, and 3x if x is greater than or equal to 7. Okay, and I apologize for having scratched this out. I just wrote something down wrong at first. So I'm going to zoom in real quick, take some time, look at that just for a second, write it down. And let's.
What did you name the second one? If 0?
Oh, if 0 is less than x is less than 7.
Okay.
Right? Or if x is between 0 and 7. So this thing looks a little bit complicated because there are 3 equations all wrapped into one thing that we're calling a single function. This is a single function called f of x, but the values of this function are determined by 3 different equations predicated on 3 different conditions. Okay, so what do I mean by that? Let me color code this. This first equation can only be used when the input values are less than or equal to 0. This second equation, I'm color coding in pink, can only be used if your input values are between 0 and 7. And finally, this last equation or expression can only be used if your input values are greater than or equal to 7. So this is very much like what I was saying on Monday, where functions can operate like vending machines, where depending on the input, that will determine what kind of snack you're going to be able to afford. Not all snacks have the same input values, right? So any input value x that's less than or equal to 0 will allow me to use this equation to figure out what the output value is. If I choose an x value that is between 0 and 7, but not including 0 or 7, so like if I chose an x value of 1, then I can use this equation to determine the output value. But I can only use one of these 3 equations, and I have to choose which equation based on what my input value is. Does that make sense? Okay. Well, let's practice evaluating the function at different inputs. Okay, so we want to find the following. F of -3. We want to find f of 0. I want to find f of 2 and f of 10. So sort of based on what we did last time, if I was trying to evaluate this function at f of -3, what do I have to do with this -3?
Substitute it in for x.
Yeah, substitute it in for x. But piecewise functions are a little bit strange because we have 3 equations that we could substitute this into. So a lot of times what I'll notice each semester is that students will just plug it into every equation and then try to guess what the answer is there. But you have to pay really attention to what the rule here for the input is. So if we think about this like this is a particular coin that we're dropping in the jukebox. And the type of coin is going to allow us to play one of 3 songs. Okay. Based on this input, what song are we allowed to play?
The first one?
The first one. Because -3 is less than or equal to 0. -3 does not belong between 0 and 7, not on the number line, nor is it greater than or equal to 7. So a lot of moving parts here, right? It is very much like a machine. And we have to be able to trace, once you drop that coin into the jukebox, what song gets played. Okay, so if we know that that first song gets played, since -3 is less than 0, then what you can do is just write 7x plus 2 here, just as a warm-up, right, to get you started, so that you choose the correct equation. Go ahead and plug 7 times -3 plus 2 into your calculator, and then we'll get our final answer. Seven times -3 plus 2. And what do you guys get when you do that?
Negative 19?
Yeah, negative 19. Good job. So the function value evaluated at negative 3 is negative 19. Now let's do the same for 0, right? 0 is the coin that we're sticking into the jukebox. So what song are we going to be allowed to play? We have 3 songs.
I know the first one, but I don't know.
First one? That's what I was going to say too.
Yeah, it's exactly the first one, because the first one says x can be greater than, x can be less than or equal to. And since our input is equal to 0, we'll go ahead and use that first equation. So 7x plus 2, which tells us we're doing 7 times 0 plus 2, which that one should be equal to 2. Does that make sense? Okay. What about this third one, f of 2? So what song am I going to be able to play here?
Song number 2?
Song number 2, right? Because 2 is between 0 and 7. So I'm just going to write as a guide 7 minus 7x. And then I can go ahead and evaluate this at x equals 2. So 7 minus 7 times 2, which is going to be, is it negative 7? Yeah, negative 7 there. Since that second song is color-coded pink, I'll box that in pink. And then finally, for the last input value, this input allows me to play which song?
Song number 3, because it's greater than 7.
Yes, exactly. So that's exactly the logic you should be using as you approach this problem. You'll want to slow down. You got to slow your mind a little bit and then really think hard about which equation you're allowed to use based on the input. And then 3 times 10 is equal to 30, right? So most times functions are given by a single equation, but that's not always going to be the case. So when you're up against a piecewise defined function, then we have to slow ourselves down and choose which is the appropriate equation based on the input that was given. Okay. And in reality, we have a set of x values. Here is an x value that's tied to a y value. We have another x value here that's tied to a y value. We have an x value here that's tied to a y value. And we have an x value here that's tied to a y value. So knowing that, you could sort of imagine where we're going here. We're going to graph this thing. Okay. And just as a preview, because we have 1, 2, 3 sections or equations that make up this one function, our graph is going to have 3 parts. Okay. So let me rewrite this function just so that we have it on hand. Our function that we're dealing with is a piecewise defined function that has 7x plus 2 if the input values are less than or equal to 0, 7 minus 7x if the input values are between 0 or 7, and then 3x if the input values are greater than or equal to 7.
And they'll always be like that? That's like the formula?
Yeah, I mean, this is what piecewise functions look like.
Okay, okay.
The equations here might be different. The input conditions might be different, but it would always have more than one equation here. And the input rule will tell you which one, based on the input, which equation are you allowed to use. Okay, so if I was trying to graph this thing, I'm gonna draw a big graph space here. I'm gonna color code this the exact same way I color coded it before, where the first one's purple. The second one is gonna be pink. And then the last one, hopefully the orange is turning up on the on your monitor. Okay. Graphing a piecewise function is a little bit more involved than just graphing a function. Okay. But it's fundamentally the same rules. Okay, so let's see this. My inputs here are, let's go with 1, 2, 3, 4, 5, 6, 7, 8. This is -1, -2, -3, -4. Hopefully that's good enough. Okay. What I would say is that if we're going to graph these things, we need to make 3 tables, one for each part of the graph. Okay. So I'm going to start with the first equation. We have an x value, and we have a y value that's determined by 7x plus 2. So we get to choose our inputs here, but we need to choose inputs that follow this rule, that are less than or equal to 0. So that means that basically here at our x value of 0, we're going to be splitting our graph up. So I'm going to put a vertical line there, because at x equals 0, we're going to have some part of the graph that's over here, that's less than 0 for our x values. So this is at x equals 0. Then we have some portion of the graph that's between 0 and 7. So I'm going to go out to 7 and say, okay, I'm just going to put a vertical line here. And that's x equals 7. And these are just to reference the portions of the graph that we're going to be drawing. Okay, so we have basically one section here, and one section over here that will correspond to these 3 sections of the entire function. So again, one section of the function uses x values that are less than 0. The other section uses x values that are between 0 and 7. And the final section uses input values that are greater than 7. Okay. Does that make sense? So for the first part of the function, we're just going to choose values that are less than 0, less than or equal to 0. So what I would say is always use this value here. So I'm going to start with 0. And because we have less than or equal to, we're going to use a closed circle when I plot this. Okay, so this little dot here, is going to be important. When I use 0, I'm going to use a closed circle because that's going to be included in this section. Well, I think we plugged 0 in already. When we plug 0 into this, we get positive 2. So that's our y value. And then I need to choose another x value that's less than or equal to 0. Well, let's go lower than 0. And I like to give myself a little bit of space. So I'm going to choose a value that's less than 0. I'm going to go with -2. That's going to be a closed circle as well because that is less than 0. Okay, so it's like following the input rule. It's a valid x value. It's a valid input. And now when I plug this in, 7 times -2 is -14 plus 2. Go ahead and throw that in the calculator because there's a lot of moving parts here and we can't be bogged down with the arithmetic too much. So 7 times -2 plus 2 is -12. So I have an x and y pair there. So what I can do now is go ahead and plot 0 and 2, 0 and 2, and that's a closed circle. So I'm going to put a closed dot there. And then -2 and -12. Well, Lord, I didn't draw this low enough. So let's go ahead and call this -8, -9, -10, -11, -12, all the way down here. Okay. And I just use this dashed line to sort of make sure that I'm relatively straight when I draw this. And now what I can do is connect these two dots like so with as straight a line as I can get. Okay, and I'm using a straight line here because this is a linear function. Y equals mx plus b. In fact, all three of these are linear functions. Again, another way to tell whether something is a linear equation is by checking the exponent on the variable. And the exponent is 1 here, and 1 there. Okay. Okay. So for graphing any line segment, we just needed those 2 points. But now we need to do the second graph or the second part of this graph and then the third part of the graph. So we're going to need 2 more tables. So I'm going to make a table over here. I'm going to do it in pink. So x and y. This time y is going to be determined by 7 minus 7x. And I need to choose some input values that are between 0 and 7. So choose x between 0 and 7. But here I'm going to guide you. You don't want to choose something between 0 and 7. We're going to go ahead and choose 0 and 7. Zero and 7. Does that seem funny to you guys?
Yes.
Why does it seem funny?
Why did you decide to pick those?
Well, because they were given to me.
Okay.
But does it seem like this sort of suggests that I shouldn't be able to do that?
No, I guess not.
Well, what I'm trying to draw your attention to a little bit is that I really shouldn't be able to choose these values for this equation because it says that x has to be between 0 and 7, but I don't have less than or equal to. There's no equal bar here. But I'm choosing them anyway because I'm a maverick and I do what I want. No, we're doing it because it's going to help you out. Trust me. I think that that's the easiest way to go with it. We want to see what happens at these endpoints, but we have to be conscious of the fact that these endpoints will not be included. So when I plot these points, I'm going to use open circles for those endpoints. Okay, so we'll go ahead and plug these values in and see what our corresponding y value is. So 0 times 7 is 0. So this is going to be positive 7 here. And then we throw a 7 in there. That'll be 49. So what would this be? 42? Negative 42? Lord, way too big. 7 minus 7. Yeah, negative 42. Okay, well, that's great. We'll start here with an open circle at 0, 7. So 0, 7 is going to be 0 up here, Lord. And then this part of the graph, sorry, from 7 to 42, it's going to be like way up here, way larger than the graph space that I've given you guys. So let me go ahead and draw this over again, but give you guys better scale. Okay. Didn't realize that the output values would jump up that much. Our input values are fine, but the output values are crazy. And we're already jumping up to, oh no, it would have been lower because it's negative 42. Okay. So maybe I'll go by 7s on the y-axis. So 7, 14, 21, 28, 35, 42, 49, negative 7, negative 14, negative 21. Just, I'm trying to do the multiplication in my head. It's just easier to do this. Negative 35, negative 42, negative 49. Okay. And I think we were fine going 1, 2, 3, 4, 5, 6, 7, 8. Gonna go out here to 9. Sorry about that. Negative 1, negative 2, negative 3, negative 4, negative 5. Whoop. That should be good. And our first 2 points were at 0 and 2. 0 and 2 is somewhere in here. So let me say that this is like 3.5. So right here, 0 and 2. And then we had negative 2 and 12. That would have been like here-ish. Now our scale looks a little bit better. Then we said for the pink part of the graph, we have 0 and 7, which is here, but it's an open circle. And then 7 and negative 42, which is 7 and negative 42. Which is an open circle as well. And then we're going to connect those endpoints with a line like so. And then finally, we might as well continue the work on this page where I have to do my last table, which is x and y is equal to 3x. So we're going to choose input values where x is greater than or equal to 7 here. So what I'm going to do is choose 7. And that's going to be a closed circle. And I'll just choose 8. And that's also going to be a closed circle because they do follow this rule. They are both greater than or equal to 7. So this value, when I plug in 7, will be 21. And this one will be 24. So we have a set of ordered pairs there. And we can plot those. They're both closed circles. So we have 7 and 21, which is up here. Right about there. And that's a closed circle. And then 8 and 24, which is probably here. Closed circle as well. Connect those with a line. Not the prettiest thing, right? But what we're trying to get at is that we had these 3 equations. And when we graphed 2 points for each section, well, we get this line segment here, this line segment here, this line segment here. Okay. And technically the points on the end can continue on in this direction forever. But that's going to be the process for graphing one of these things. The choice of scale is important. Let me say that. Choice of scale on the x-axis and y-axis determines how, let's put it this way, how pretty the graph looks. So what I would recommend, which is something that I did not do here, is that we might look at the output values first. We have an output value of 2 and negative 12. We have an output value of 7 and negative 42. An output value of 21 and 24. So the output values tell you how far you're going to have to travel in the y direction. So if my lowest output value was negative 42 and my highest output value was 24, then I should have kept that in mind when I made the scale, right? I should have counted by like 5s or 10s, something that would allow me to get down to negative 42 and up to 24. The same thing with your input values. If your input values are spread out, which all of our input values were sort of between negative 2 and 8, then that tells me that I could have counted by 1s or 2s, and just finding a good set of input values so that, or input and output, the scale, just so we can get a nice picture. But this equation is based on that 7x plus 2. This part of the graph is based on the 7 minus 7x. And this part of the graph is based on 3x. Okay. Does anybody have any questions? I know that was sort of a roller coaster ride. Okay. Well, this is what I want you guys to do. I'm going to give you a different piecewise function, and I want you to graph it. So take some time and graph this thing. We have f of x is equal to 2x plus 1 if x is less than 6, 5x if x is between 6 and 10, and 6 minus 6x if x is greater than or equal to 10. How are you guys doing so far?
I have a question on your first table. I
Yeah.
mean, we could pick anything for X as long as it was less than 6, right?
Yeah, I would always start off with 6 and then definitely choose anything that's less than 6. So if you chose 5, that would have been fine. Anything.
And if I didn't choose 6, what if I chose like 1 and 2?
You want to definitely choose the endpoints.
Okay.
Because we sort of want to know what is happening at the endpoints. So I would say, let me write a little note here. Always choose the endpoints. Because for some of the graphs, like for this first one, we want to know what happens as we get very close to 6. I know that 6 is not included technically, but the thing is, like, I could choose 5.9 or 5.999, and even though those are very close to 6, they're still technically less than 6. So I want to see sort of what happens as we approach 6. That's why I'm choosing 6 here. I just have to be mindful about using an open circle since I know 6 is not included. But you'll choose whatever number this is here, and then anything lower. And
Okay.
then for the next one, I chose both of those endpoints. But since those are included, since I have these little equal bars, I can go ahead and close those up with closed circles. And then for the last graph, I know that x has to be greater than 10. So technically, I'm not supposed to choose 10. But I want to see what happens when I choose something real close to 10. Like if I had chosen 10.1 or 10.001 or 10.00001, those all would be close to 10 and greater than 10. So that's why I'm choosing
How would
those.
you want to pick those type of numbers?
Why would I want to choose those types of numbers?
Mm-hmm.
Like a 10.001?
Yeah.
Because I want to see what is the behavior of the graph as I'm getting super, super close to that endpoint. So instead of choosing one of those weird numbers, I say just choose the endpoint and just make it an open circle. Because like if you chose 1 and 2, for instance, you would just be getting this little segment over here. But the domain, really the domain of this graph goes all the way very close to 6.
Gotcha.
Yeah. In fact, this idea that I'm talking about, like trying to get really, really, really close to a value, is a concept that's called the limit as you approach some x value. And that concept is used a lot in engineering and higher mathematics, but there's really, it's not sort of incorporated into this class. There's really no time to really get into the philosophical reasons of why that concept exists. So I'm just saying, choose the endpoints, use these numbers that they give you. But for this one where they only give you one number, well, then just choose another number lower. And then for this one, since they've given you 10, use 10, but then use something bigger. But in any case, when you draw this out, you should be getting a picture that looks something like this, where this arrow looks like it's going down. That purple, the first function, the first graph. The second part of it looks like it's going up, but it's raised up and broken off, not connected, right? It's disjoint. You would call this a discontinuous graph, right? But it's up here, and now that looks like it's going up. But then for this third region, it starts off way down here as far as its input values. So you should be finding something that looks like this. Doesn't have to be exactly right and exactly to the right scale, because I chose my x-axis to be scaled by 4s, and I chose my y-axis to be scaled by 10. So depending on how you scale it, that'll determine basically the distortion of the graph. But roughly speaking, you should have these 3 components. So I think with that being said, let's go ahead and take a 10-minute break. We'll come back at 2:10 and we'll start up on some more stuff. Okay. So in this next section, section 2.7, you get thrown, it's going to feel a little bit like you're thrown into the deep end, but it's just because it's some new stuff. And whenever you see something for the first time in math, it's always really daunting. But what we're going to have to do in this section is we're going to be exposed to some of these common functions that we see over and over again in college algebra. Things like linear functions. And we've already had experience graphing some linear functions. They just form straight lines usually. They can have different slopes. They can have different intercepts. But we call these things parent functions because these are the basic forms of the function that once we do some manipulations of them, we can perform some operations on the functions, like multiply it by a number or add a number. It'll change the behavior or basically shift this graph around in the graphing space, right? Because not all linear functions have an intercept that go through the origin. Sometimes they're a little bit higher, sometimes they're a little bit lower. The same thing with quadratic functions. When you end up graphing a quadratic equation, you get this characteristic U-shaped thing, which we call a parabola. The parabola can be like a right side up smiley face, or it can be sort of rainbow shaped where it's sort of upside down. There's also things like cubic functions, which we didn't see cubic equations, but we did see quartic equations. In any case, they generate these graphs of functions that we're going to have to be able to identify just by looking at them. Like so, for example, when you see something that is a straight line, we'll be able to identify that as a linear function. When we see something that's sort of U-shaped, we'll think about that as a quadratic. Something that's a little bit wigglier like this, we'll think about that as, oh, that must be the parent function is a cubic function. And even if it looks a little bit more warped or stretched, we're always going to go back to these parent functions as the reference for which we'll start to analyze the graphs of other, maybe more exotic functions. Okay, and these parent functions are something that you're going to have to sort of memorize like flashcards. And I put that handout in Canvas on different parent functions. So let me go ahead and share that real quick. Let's go ahead. Boom, boom, boom. There we go. So graphs of common parent functions. When you go into Canvas, you should see something, this page here. You could maximize it if you wanted to. But you see that there's different parent functions here. We have a linear parent function here. It has some information about the domain and the range. But what's really important here is getting used to the general shape of these functions. So if I see a function that, for instance, looks like this, maybe it's a little bit steeper, like this blue line that I've drawn, and it's a straight line. Well, then I should know that that comes from this parent function. It's a linear function. If I see something that's sort of U-shaped like this, even if it's upside down, I'm going to have to, put the face to a name and say that that is a quadratic function. Same thing with this cubic function. If I have something that maybe looks flipped around but has the same behavior, I'll think about it as a cubic. So this page is here as a reference, just so that you can familiarize yourself with the type of function it is, what the parent function is. But a lot of times you'll get something like, let's say we have an equation like y equals x to the third power plus 3x minus 17. I have no idea what this looks like. But if I were to graph this in Desmos, for instance, if I throw it into a graphing utility, there's Desmos, then it should spit out something that's roughly shaped like a cubic function, because I can tell that this is a cubic by looking at the highest exponent on the variable. Okay, so knowing this, I will say this guy over here is the parent function. So it should look something like that. Okay. So again, it's sort of like we're going to have to just become familiar, maybe with flashcards, with what these equations look like by generally assessing what the parent function is. Okay. But today we're going to focus primarily on this quadratic function. And then we'll look at the square root function here, because we're going to do some transformations to each of these functions. And there's some simple rules that determine how we can transform and manipulate the graphs of the functions by manipulating their equations. Okay. Boom, boom, boom. Okay. So actually, one more note about these. These kinds of equations that I gave you an example for here, these little pictures, these are called polynomial equations. Or polynomial functions, rather, since we're calling them functions now. So if you can tell by looking at the equation that it's a polynomial equation, well, then the function is a polynomial function. Okay. So let's examine the function f of x is equal to x squared. Now, if you were to come up with a list of x values and y values, we could just choose some inputs, plug them into this equation, and then it would spit out our output values. So let me just choose -4, -2, 0, 2, and 4. I always like to choose some negative values, 0, and then some positive values, just so we can get a good picture of what this graph will look like. And then I'll draw a rough sketch of what this graph looks like. If I plug -4 into this equation, right, we could just grab our calculator and just chug that real quick. Plug and chug, that'll be -4 squared is +16. -2 squared is going to be +4. 0 squared is 0, 2 becomes 4, and 4 becomes +16. Okay. So it looks like the output values get pretty large pretty quickly. Like the input values that I choose here went from 2 gets transformed to 4, 4 gets transformed to 16. So if I plot these out, I could say, okay, let's go by 2s here. So 2 and 4. And then this will be -2 and -4 over here. And then for the output values or the y-axis, let's go by 4s maybe. 4, 8, 12, 16, 4, 8, 12, 16. Not super pretty, but when we plot these points, we should get -4 and 16, -2 and 4, 0 and 0, 2 and 4, 4 and 16. And it sort of looks like a V shape, but if you were to graph this into Desmos, you would see that this is a naturally curving function. So you can always graph the equation if you want to get a good idea of what the picture looks like. Okay. But say we wanted to transform this function. That is, if we wanted to shift it over to the right or shift it over to the left, how can we make this graph move around? Or maybe we wanted to make it a little bit thinner or wider. Or maybe we wanted to flip it upside down. What are some of the mathematical operations we could do to get those transformations, to get the graph that we want. Okay, well, we're going to use a simple set of rules here. So let me give you the rules for transforming parent functions. So there's basically two flavors of manipulations or transformations that you can make to these graphs, these functions and their graphs. The first is that we can go ahead and just multiply the function, multiply the output by a value. So, well, actually, the easiest thing to do would be starting with addition and subtraction. So if I have the output of a value, so I'm going to put f of x. Remember, this represents the output. And I subtract a number. Let's go ahead and add a number. I'm going to say add a. What this does is it moves the parent function up a units. So whatever this number is that I add to the output of the function, it's going to have the effect of moving the graph upward. So each of these points would move up. And for a parabola, this bottom point here, we call the vertex, and that's going to be our reference point. So we can sort of follow where the vertex goes. And if we add a number to the output of the function, that is, if we add something to the y values, it will have the effect of moving the entire graph up. Okay. If you have the function output and you subtract a number, well, that's going to shift or slide the graph down. Okay. Well, we could also manipulate things like manipulating the input of the function. So if you have the function, but we take the input and add a number to the input. So here, the x, we're adding a number to the x, adding a number to the input. This is going to move the graph or the parent function. And this one's a little bit counterintuitive. It's going to move the graph to the left, a units. So if I were to add 2 to the input, I would be moving the graph over 2 to the left. For x minus a, we're going to move the graph to the right by however many units. Okay. Another thing we could do is multiply the output. So I could multiply the output by some number. So a times the output. And what that does is two things depending on the value of a. So if the value of a is greater than 1, we're going to vertically stretch the function and its graph. That is, we're taking the y values and multiplying them by some number. But if that a value is between 0 and 1, then it's going to be vertically compressed. And since we're not working with a function right now, the best analogy I can give you, if you'll excuse my hair tie, is that if we have a function, and remember that a circle is not a function, but half of the circle would be sort of like a parabola, right? If I multiplied this circle or the equation that gave us this parabola by a number greater than 1, say like 2, then essentially what I would be doing is vertically stretching, so the graph becomes sort of taller and skinnier. But if I multiply by a fraction or some number between 0 and 1, then I would be vertically compressing, so we should see the parabola get sort of wider and shorter. And I'll do another demonstration here in Desmos in a second so that it feels more like math and less like my hair tie. Okay. Then the other thing we could do is if we multiply the input by a number, then we would, if a is greater than 1, this would be a horizontal stretch. And if a is between 0 and 1, we would get a horizontal compression. Okay, but I will tell you that we're not going to see a lot of these things. We will see these rules pretty frequently. A couple of other rules that are going to be important are going to be reflections. So reflections. So let me give you an example. If I had a graph that looked like this, and I wanted to reflect over or across the x-axis, would it be okay for you guys to say that this graph, again, if we're focusing in on the x-axis being this guy, then this part of the graph, if it was reflected over the x-axis, would look like this now. Does that feel natural to you? Just visually. It's almost as though the x-axis is a mirror. So if this guy was looking across that mirror, we would get this thing. And then if we were to reflect that same graph, so let me start with that same parent function. But this time we're reflecting over the y-axis. So I'm going to highlight the y-axis. Then we should be transforming this original graph to something that looks like this. So if you want to manipulate a function to reflect it across the x-axis, I'll call this an x reflection, just so that we can be sort of use that abbreviation. Then what you do is you multiply the function output values by a -1. So usually we just put a negative in front of the function values. And then if you want a reflection about the y-axis, so a y reflection, then you multiply the input by a -1. Okay. So we're going to start just by exploring these rules a little bit with a quadratic equation. And we're going to verbally describe, I'm going to write out a description of how these transformations are affecting the parent function. So we're going to describe how the graph of the equation, so we're going to be given some equations, relates to its parent function. And here the parent function we're going to use is y equals x squared, which is a quadratic. And we just graphed this one, so I'm just going to draw a brief sketch. Should look something like that. A little bit more symmetric than what I drew, but good enough for government work. So we're going to first examine this function, f of x is equal to, let's go with x squared plus 5. Based on this equation and the rules that I just gave you, adding 5 to this parent function has what effect on the graph?
Shifts up.
Yes. So what you'll need to do here for some of these is just write that we're going to shift the graph up 5 units. Sometimes that's called a vertical translation. And translation in mathematics just means a sliding, that you're sliding to a different location. Okay, let's do another one. If I have the function here, and I say that if I have x minus 2 squared, it's still a quadratic function. It's related to its parent. In fact, all of these are children of the parent function, right? So they'll look similar to their parent, but a little bit different. But based on the rules that I gave you, if I have the input and I subtract a 2, what effect is it going to have on this graph?
Moves to the right.
Yeah. Move the graph to the right 2 units. And now let's look at 3. Maybe f of x is equal to, let's go with 5x squared. What effect does this have on the original parent function? We're multiplying a number by essentially what would be the output.
Maybe it's a vertical stretch.
Yeah, that's exactly right. It's a vertical stretch. And the language here is a little bit weird. It's a vertical stretch by a factor of 5. So let me go ahead and see if I can get Desmos up and running so we can take a look at what these transformations are doing to our graph. All right. So we said that we had this original parent function, f of x equals, we called it y equals x squared. Okay. So this is our parent function. I'm going to go ahead and make the parent function a little bit thicker. I'll change the color to black, make it a little bit thicker. Maybe we make it 5. And then I will change the y-axis is fine. Actually, I'll zoom out a little bit and scroll up. Okay. There's our parent function. Okay. Annotate. The parent is y equals x squared, which I didn't have to write again since I had typed it over there. But in any case, for our first example here, we said, okay, what happens if we take that function y equals and called it x squared plus 5. Let me make this guy thicker, so 5. Well, yeah, it sort of looks like if we get rid of the parent, we shifted up 5, right? So the rules that I gave you aren't like a lie. I have verified it here, at least in this demonstration, that if you add 5 to the parent function here has this reference point at 0, 0. It would move up to 0, 5 because we added 5 to the output. That is, we added 5 to the y value. But if we change this blue function to the second problem that we just had, which was x minus 2 squared, now we're taking the input, subtracting 2, and then we're squaring that. Well, it looks like the reference point here at 0, 0 got shifted over to the right 2 units. So the input got shifted to 2. So you end up with the same parent function, but it got moved over, slid over to the right. And if we take that parent function again, but this time, instead of subtracting something from the input, we're going to multiply something to the output. Well, just like my hair tie example, if you vertically stretch it, the hair tie becomes skinnier, right? So if we vertically stretch by multiplying our function by a 5, our graph got taller and skinnier, right? And if I multiply by an even larger number, say 100, gets even skinnier. Or maybe 500, really skinny. Okay. And I said before that if I multiplied this thing by a fraction, so like 1 over 2, should get wider. And maybe a smaller fraction, maybe like 1 over 100, super wide. Maybe we'll go something like 1 over 25, still pretty wide. 1 over 10, 1 over 4. But you see, we're going to be manipulating these functions and trying to determine, okay, what is the best representation of that graph? Now, the thing is, we might have more than one transformation. For instance, I'm going to write this down. F of x is equal to 3x squared plus 2. And let me zoom in here because I know I'm sort of small and in the corner. What do you think this is going to do to the graph if I add 2 to the output and multiply the output by 3?
It's going to go up 2 units and stretch out.
Yeah, exactly. So we would say that this should shift upward 2 units and be vertically stretched by a factor of 3. And we can see that in Desmos. I'll just leave it all in Desmos at this point. That if I go ahead and type a 3 here, it gets skinnier. There's a vertical stretch. And if I add 2, it also gets moved up to 2 units. So that would be using 2 of those rules at the same time. What about if we had negative 4x squared minus 7. What do you think is going to happen to the parent function's graph? Well, we can sort of start to break this down piece by piece. And this is the way I think about it. We have minus 7 here, which tells us the addition and subtraction parts, I think, are the simpler parts. This should shift our function or shift our parent function down 7 units. We know that when we multiply our output by a number, we should be vertically stretching. And in this case, it'll be by a factor of 4. But we're also multiplying the output by a negative or negative 1. So that rule says that we should have a reflection across the x-axis. So let's see if these 3 things come to pass. We should be seeing something that's flipped upside down. And maybe I'll stop sharing just briefly, because I sort of want to do a magic trick, right? If I know that the parent function starts at the origin and looks something like this, then based on this transformation that I've given you, a rough sketch of what I should be seeing when I throw this into Desmos is that I should move this reference point down 7 units, flip my parabola upside down because I'm reflecting on the x-axis, and then make it a little bit skinnier. So let's say that I'm going to move it down here, and the 7 is right there. I'm going to flip it down and make it a little bit skinnier, something like this. So this is what I should be seeing when I plug this equation into Desmos. Okay, so we're in Desmos. We have the parent function in already. Let's go ahead and throw this new function in. Negative 4 x squared minus 7. Well, I don't see anything right now. But if I zoom out, I can see that's exactly what happened. So we're going to use these rules to build intuitions about what the graphs of these new functions are going to look like. And that's what we mean by we're taking the parent functions and transforming them using those rules. Okay. Well, I think we're going to have to leave it there. And we'll pick up on this discussion at the top of next class. So on Monday, we'll continue talking about transforming functions and then seeing what we can do with those. Okay. So again, remember that Friday is going to be the last day to withdraw from the class. If you need to have that conversation with me, let's have that conversation. I invite you to send me a message. Let's set that up. And again, that's just for those students who are at risk of failing or are worried about where you are. If you're a high-performing student, your grade's fine. Look at it in Canvas. I'm working on updating those things. But if your grade is fine, then you should be fine going into the rest of the semester. But if you're on the cusp or you're really worried about it, send me a message as soon as possible. We just have today, tomorrow to think about it. And then Friday, probably by end of business day, you will have to have come up with that decision so that either I can initiate the drop or you communicate with your advisor about initiating that drop. Okay. It'll probably be faster if I did it. So anyway, if you need to have that conversation with me, that is exactly why I'm here. Okay. So continue working diligently on your material. You can see from this week's 2 lectures that it's getting really complicated. We're putting all of the pieces together. Okay. But we're just about to bake this cake. We're almost done with the semester. So just stick with me. Come to Math World and I'm going to try to get you through. All right. All right. So that being said, I'll see you guys next week. Have a good weekend. If you need me, you can always reach out.
Thank you.